So thank you, Jens, and welcome everyone to this first evening talk, a software design talk about type erasure. Now, you might be here for three different reasons. You might be here because there's no other talk in parallel. Still, you're in the right spot. You might be here because you've never heard about type erasure, or because you've heard about it but don't know what is hiding behind that. Then you're definitely in the right spot. Or you might be here because you actually know type erasure and you're wondering, what is different about this talk? And you're right, there is actually a couple of talks about type erasure already. However, all of these talks have mostly one thing in common. They very, very quickly jump into the implementation details and basically never leave this place. For that reason, they might actually skip a couple of very interesting properties of this technique. And this is now what I do tonight. I will talk about the design properties of type erasure. And so this indeed will be a software design talk. So I will not show a lot of very specific implementation details. I will not do a lot of no except. I will not show forwarding and R-value references. And Jason and Ben, if you see this, I will not use a lot of context for either. It will be entirely about software design indeed. Now, before I get started, allow me to very quickly introduce myself. Jens has already said, I'm Klaus Iglberger, but I'm pretty much aware that many people cannot pronounce my last name. So I'm very happy if you just call me Klaus, and I'm just happy that you talk to me at all. So I'm just Klaus. And I'm actually working as a C++ trainer / consultant. And in that job, I very much like to talk about software design, because I personally consider this to be a very, very important topic. And that will actually be the first part. A couple of slides about what is the challenge of software design. After that, I will not immediately jump into type erasure, and how this sounds disappointing, but I actually want to build this up. I first want to talk a little bit about how we can solve problems naively, and you'll be super disappointed after that. Then we'll actually try to solve this better in a classic way by means of design patterns. And then after that, so in approximately 20 to perhaps 25 minutes, we'll actually jump into type erasure. But by that time, you have a very good understanding what we're actually looking for. So, the challenge of software design. Why do I feel this is such an important topic, such a basic topic? And essentially, it's about the general problem that all of us face, all of us software developers, the problem that we actually have to deal with daily. And that problem is change. Yes, the one constant in software development, change. Yet change is not a problem in itself. It's actually the truth in the industry that software must be adaptable to frequent changes. It is expected that things change. And as a side remark, this is actually the reason why software is called software. It is supposed to change. It is supposed to easily adapt to any kind of requirements change. Yet, of course, you are aware that it might not be that way. No, actually, software sometimes does not feel easy to change. On the contrary, sometimes you pick something that sounds easy, but 2 weeks later, you realize that actually this was quite a difficult task. There is something that makes our life so much harder. And that's the thing that is actually the bane of a software developer. The thing that we are always haunted by, dependencies. And of course, I'm not talking about the necessary dependencies. At some point, things need to work together. At some points, there is natural intuitive dependencies, but I'm talking about the artificial dependencies. Those things that really make things so much harder, that make change so much harder and so much more difficult. And that is exactly what we want to change. This is exactly what we want to minimize. Just to give you one idea how bad this actually is, a quote by Ken Beck, kind of the inventor of TDD, dependency is the key problem in software development at all scales. So indeed, this is the problem that we have to face on a daily basis. Change is the motivating, the driving force, but dependency is the real problem. And so let's take a look at how dependencies build up. And let's introduce a toy problem, and let's try to solve it a little naively by simply using inheritance. And the toy problem for this evening is shapes. Yeah, okay, I know. This is already where some people move to the other talk. That doesn't happen in parallel, but still, a lot of people are now disappointed. Oh, such a boring topic. I agree. It's kind of simple. But perhaps this is exactly why I've chosen this problem. It is simple. I will show a technique that you've potentially not seen before, and so a simple problem actually might help to wrap your mind around all of the details. And just to express it in the words of my co-organizer of the Munich user group, I'm tired of this example, but I don't know any better one. Yes, of course, we would like to have something better, but it's a nice teaching example, and so I'll stick to this one. So I start with a shape hierarchy. We start with a base class called shape, which comes with a draw function. And of course, this now needs to be implemented in many different kinds of shapes. So for illustration, I'm using circles and squares, but please imagine that there's many more. Ellipses, rectangles, ovals, you name it. Circle and square implement draw, which from a design perspective is already something that is questionable. Because if you truly want to draw, you might actually reach out for a graphics library. That graphics library, say OpenGL, 3DX, anything, might now actually introduce quite a heavy dependency on circle. That is something that is, of course, pretty undesirable. A circle should not be a heavyweight construct that depends on a graphics library. Of course, it should be lightweight. Having said that, an obvious solution is to use inheritance. One more layer in this inheritance hierarchy. So let's just do not introduce draw in circle, but let's have an OpenGL circle. That idea also gives us the ability to actually use different libraries easily, like the metal circle, using the metal library instead of OpenGL. Yeah, you can imagine that there's many more implementations, different kinds of draw implementations. Pretty nice. And of course, it happens on the square side just as well, OpenGL square and metal square. This might work for some time, but it probably becomes a little hard to maintain as soon as we introduce another function, say serialize. So we want to turn this shape into a byte pattern, and of course later retrieve it from file or database and deserialize it again and recreate the shape that we've actually stored. Now, how do we implement this serialize? Well, it's the same problem again. Of course, we don't want to do this in circle or square. This would create dependencies. How do we do that? How do we use little endian or big endian? So there's a solution. Inheritance. We could just introduce another layer in this hierarchy and introduce something like the OpenGL little endian square or the OpenGL big endian square. That is where I implement serialize. Very nice. And of course, in metal square, we do the same, which, however, already starts to look complicated on one hand side, but also feel wrong because I now implement serialize twice. Right. Perhaps another approach helps, and also probably because this hierarchy starts to become pretty deep. Now this has already 4 levels. Perhaps you should just keep it flat and just implement all of the necessary variations in that form. So a circle just gets a OpenGL little endian circle and an OpenGL big endian circle and so on, all the variations. But also this does not really help with duplication. Now the draw function is implemented twice, so every version of draw and also, of course, every version of serialize. It doesn't feel right. It doesn't feel good. So if indeed we use inheritance naively to solve a problem, this pretty quickly leads to code that we just don't feel is good. There's many derived classes. And let's be honest, with pretty ridiculous names. Now, this was only 2 functions. Imagine the names of 4 functions. Not a lot of fun now. We have a pretty deep inheritance hierarchy quickly. After just 2 functions, we had a level depth of 4. This truly quickly grows to something that we cannot really manage anymore, not even understand anymore. There's a lot of duplication also. This is what I tried to point out. It's not really clear where we should put the one implementation, and it's definitely hard to add any other function. We don't want to even think about adding a third function. That would create a total mess already. And so maintenance is definitely not a lot of fun. I would actually rate this as pretty hard. So what do we do? Well, to quote the pragmatic programmers, Andrew Hunt and David Thomas, inheritance is rarely the answer. What you should do is we should delegate to services has a trumps essay. And so we reach for the right kind of solution. We reach for a design pattern. The classic solution to actually solve this kind of dependency problem and this kind of complexity issue. And the design pattern that I'm now reaching for is coming from this book. The book that most of you have seen before, Design Patterns, Elements of Reusable Object-Oriented Software. That is the so-called Ganger 4 book. Ganger 4 because of the 4 authors. And it is the origin of 23 of the most commonly used design patterns. Just as a reminder, general reminder, what is a design pattern? A design pattern is something that has a name. And that name expresses some intent. You want to detangle, you want to decouple software entities in a very specific way. You have an idea how things evolve, and this is why you choose a specific kind of pattern. That is what the name and the intent contain. Almost all of the design patterns aim at reducing dependencies. There's actually at least 2 in this book that I don't really count as design patterns. This is another talk, however. They usually aim at reducing dependencies, and they, for that reason, provide some sort of abstraction. Something that allows you to actually separate concerns. And last but not least, a design pattern has proven to work over the years. So it's not something that falls from the sky and suddenly works. No, it definitely has to prove that it works in many code bases. This book is a collection, not something that these 4 people invented. Now I'm choosing one of the most famous design patterns from this book, the so-called strategy design pattern. Now, I don't assume that all of you are totally familiar with strategy, so here is a short reminder. On the left-hand side, we have the circle class. The circle class that we've seen before in this hierarchy, and indeed, this is now representative of any concrete shape. Could be square tooth, could be triangle, could be rectangle. It's a concrete shape, it's not a base class. In this class, we have this draw function, which, as we said before, creates some kind of dependency, something that we would like to extract. We have realized that we would like to have many implementations of draw, and so we should not have it inside the class. We should extract it. And this is now what we do by means of the strategy design pattern. We introduce another hierarchy, and instead of direct inheritance, circle now owns the strategy. So it has a relationship. We might now have a pointer to a strategy. This class is now the abstraction of how to draw a circle. So there's a draw circle function that we can now implement in various ways. That is an application or now an adherence to the so-called single responsibility principle. We extract the thing that changes, the variation point, and by that we actually gain all of these advantages. We can now implement an opengl strategy, a metal strategy, a 3DX strategy, anything we like. And we actually don't have to draw. We can also just do something for testing, a test strategy. That is something that we can now pass from the outside. We call this dependency injection. So from the outside, we give the circle the thing that it should use to draw itself. And so its circle doesn't depend on that anymore. We've broken that dependency. And as last remark, we kind of now also fulfill the so-called open-close principle because we can now implement any kind of strategy easily without having to modify any existing code. Once this is in place, we are free to add whatever we want. Very good. Now, just as a side note, because you might now have this idea that it's always about inheritance, etc. No. The strategy design pattern is not limited to object-oriented programming. Definitely not. And it's also not limited to dynamic polymorphism. And last but not least, it's also not a language-specific idiom. The standard library itself is actually full of examples of the strategy design pattern, but all totally without inheritance, without base classes, static polymorphism. So for instance, you know that from a lot of the standard algorithms, like accumulate. So I can accumulate numbers, and I specify how I want to accumulate. That little plus here is actually a strategy, a compile time strategy. You specify from the outside, by means of dependency injection, how this accumulate should work. Or standard vector. Yes, the second template argument is actually a strategy. You specify from the outside how allocation should work. That's a strategy. And of course, this is true for all containers. And some containers actually have more than one strategy. Now, uno.z has even three: the hash, the key equal, and the allocator. All of this are customization points. You can specify the behavior from the outside. Strategy. And of course, unique pointer also. A unique pointer takes a deleter. That is a strategy. So the standard library is full of strategy. It's one of the most used design patterns, and it definitely always helps. So let's apply that to our toy example, to the drawing shapes example. Now I start with a glcolor. That little piece of code is now supposed to represent some dependency on opengl. It's an example. So it's small, it's something that is not very specific, but please imagine that this could, of course, be something much bigger. It represents this dependency only. All right. Now, we have this shape base class. And I said initially that we would like to draw and we would like to serialize. Both of this is pure virtual functions. So all the classes that implement that need to implement draw and serialize. Now, before I implement anything else, I introduce a draw circle strategy. That's a long name, true. But that is now the abstraction of drawing a circle in a very specific way. So this draw function takes a circle, potentially many more arguments. It indeed can be a couple more. And that, of course, again, needs to be implemented by deriving classes. That is now the class that the circle uses. In the constructor, for instance, or alternatively by means of setters, I pass a draw strategy. Now, I could do this by means of a unique pointer. And I could say, so here's circle, this is your dependency, this is how you draw yourself. Please remember it. So you own it. We move the strategy into our data member. So we own a strategy. And whenever somebody calls draw, by means of some arguments, of course, we simply forward this request to our drawing strategy. So we call this draw, we pass ourselves all the arguments that are necessary, and we can draw ourselves. Nice. So we now have no dependency on opengl anymore, no dependency on any graphics library. We are given this dependency from the outside. Really useful indeed. So circle is not depending anymore. Okay. Note, yeah, there's no specific dependencies on any graphics library. Of course, the same happens for squares and all the other shapes. So we have a draw square strategy also. And note, indeed, it is two classes. It need to be two classes, else we have accidentally coupled all of these kinds of shapes together. So I have a draw square strategy that provides a draw function for squares, and that is what Square now works with. It's the same thing. In the constructor, I get such a strategy. I move it into my data member, so I take ownership. And whenever somebody calls draw, I'll just use that in order to do whatever I'm supposed to do. However, I'm supposed to draw myself. Now, with this in place, I can now finally introduce any kind of strategy. So opengl strategy for circles. We can have the opengl square strategy. All of these now truly use opengl. So here, this is the representative. They may have an opengl color or whatever. That class now is highly depending on opengl, on that specific graphics library. Not circles, not squares. They are totally oblivious of that dependency. And of course, at some point, I put all of this together, and that happens now in the main function. And I might have a vector of unique pointers of shape. I create an empty vector, and I put all of these things inside. So I create a circle, I pass the radius 2, and I create an opengl circle strategy. Give it a color. That's the second argument, the strategy. I do this for a square 2 and for another circle, and I might draw all the shapes in that vector. Nice. Indeed, we have actually managed our dependencies. Very good indeed. That is, I would say, a first true solution to the problem. Let's take a look at the design. As I said, the thing that is most important to me. What we have in this situation is actually 3 levels of design. In the highest level, which is considered to be the one that is most stable, the one with the lowest dependencies, we introduce this shape base class. That allows us to, on another shape, let's call it the middle level, to introduce different kinds of shapes, like circle. And that, on that same level, I introduce the according strategies, draw circle strategy. Now, of course, it requires knowledge about this circle. But that class in itself allows me to, on yet another level, the lowest level, the level where I expect most dependencies, the code that also changes most often, on that level, I can now actually implement any kind of strategy. So I have properly separated concerns. I have an architecture. I have something that can actually maintain for a long time. Absolutely great. Super amazing. We're much, much more happy than this naive solution that we had in the beginning. And it's actually a good job. We have extracted the implementation details, essentially the single responsibility principle. We have created the opportunity for easy extension. So we satisfy the open close principle with regard to both the different types and different draw implementations. And we have properly separated interfaces. We have 2 strategies, one for circle, one for square, and of course, one for all the other shapes. And we have definitely now dealt with the duplication. There's one place where we have the implementation for drawing circles, one place for dealing with squares, etc., etc. Proper design. And also, we have definitely limited the depth of the inheritance hierarchy. Big win from my perspective. So maintenance is much easier now. Definitely much better than before. Great. But I can imagine that you're still not happy. C++ programmers tend to be pretty easily unhappy, and that is potentially because you're thinking about performance. And yes, in C++, this is one of the first arguments, and I agree. There is a couple of things that actually have a very negative impact on performance. First, we've just introduced a second indirection. So we have the pointer to shape, but that shape now contains a pointer to some strategy. In order to draw a shape, we have to call 2 virtual functions. That may become expensive, especially for simple operations. Drawing is probably a little more expensive, but there's other things that for these things, it might be too expensive. We have seen that in the main function, call a lot of make unique. Now make unique all over. Of course, make unique is great, but of course, in this situation, it means that we are doing many, many tiny allocations, mini allocations that essentially just result in a lot of pointers, a lot of indirections. And so, yes, that is, of course, the reason why I use unique pointers, automatic memory management, but still, it's not nice. It would be so much nicer if you could just get rid of all of that. Then, design aspect, again, I've shown the draw stuff. I've not really talked about serialize anymore. Of course, we have to do the same, exactly the same for serialize as well, which means that we suddenly have 2 pointers and more base classes, more inheritance, more virtual function, more pointers. It's just more of all the things that we do not particularly like. And okay, we have to manage the lifetime explicitly, which is done by unique pointer. That is true. But that doesn't automatically make it modern C++. Not really. Throwing a couple of unique pointers at a solution doesn't make it modern. It still feels old. It is old. It is the 90s solution. I said there's a lot of hierarchies. Indeed. Think about the serialized stuff also. And still, something that I personally feel is a design issue circles, squares, and all the other shapes still know exactly about all the operations that we can run on them, like draw, serialize, and potentially many more. Yes, we have extracted implementation details, but we have not really extracted the knowledge about these affordances, to use the terminology of Arthur Dwyer. We still know about all of these details, and that actually creates all of this unnecessary overhead. How much nicer would it be if we could completely extract this knowledge? How much better it would be for us if a circle would just be a circle and everything else is just plugged in a different way? And how much more modern would it be if we would use a value-based solution? Not something based on pointers, but really values that can be copied, that can be moved, that actually provide a much easier way of dealing with things. So, and this is now finally the point where we actually start to use type erasure. You have now seen that this old stuff works, but it doesn't make us happy. So let's rethink that. One of the first talks you might have seen or heard about type erasure is this one. Inheritance is the base class of evil, a classic. It's just approximately 20 minutes long, but this is a talk where in a very, very quick way, John Parent actually shows how type erasure can work. Because that is one of the first talks, a lot of people believe that this is where type erasure was invented. But I have actually found a paper from the year 2000. And I believe that is the paper where the very first time this technique was described. And it was described by Kevlin Henney. So I, truth be told, believe Kevlin Henney is actually the inventor of this type erasure technique. So take a look at valued conversion. It's truly an eye-opener, very well written. And it, for the first time in 2000, describes stood any. Now, just because the term type erasure might be something that you've heard differently before, what is type erasure and especially what it is not? So type erasure is not a void pointer. Now, a void pointer is a void pointer. This is not a technique. This is not a design. It's a pointer to no type. It's also not pointer to base. That's what we call a base inheritance relationship. That's not type erasure. And for me personally, most importantly, type erasure is not a variant. Stood variant is also a design technique, kind of. But it is a design technique that is 100% orthogonal to the thing that we are doing right now. So standard variant is something you use if you want to add operations easily, not types. What we are after is adding types easily, not operations. So it's exactly orthogonal, so it's definitely not a variant, what I'm now using. So if you used that term before for these three things, please stop. It doesn't make sense. Type erasure is, first, a templated constructor. That you will see is super important, and that definitely makes it so powerful. Second, it's a completely non-virtual interface. We are now creating something that is dynamic polymorphism, but indeed we will not have openly any virtual function. And it is a mixture of three design patterns. A design pattern called external polymorphism, the bridge design pattern, and the prototype design pattern. So let's take a look at how exactly this technique works. And again, I get started by my representative of some dependency. So again, a representative for opengl, the opengl glcolor. So again, it's just representative, but that thing must not appear in the things that cannot depend on opengl. It must again appear at some place where we can actually deal with that. Second is a circle class. And yes, that's it. That is the circle class for the rest of this example. And note, there's no base class. There is no virtual function. There is no draw function. There's no serialize function. There's no pointers. There's nothing. It's just a very basic circle. It's a circle that I could show on, let's say, day 3 of a beginner's training. Very, very straightforward indeed. It just represents a geometric primitive. No dependencies whatsoever. And exactly the same is true for square. No base class, no virtual functions, no dependency on any operation, on any affordance. Very simple. So once again, no base class. They don't know each other. They're totally independent, totally unrelated. They don't know about the operation, and they definitely do not depend on any implementation detail. How then, do you ask, can we actually abstract from these? And how do we add the knowledge about drawing, etc.? Well, that is something that we package differently. We package this into these two structs. And yes, it's structs at this point. Don't worry. In a couple of minutes, this will not worry anymore. I have a struct called shape concept, which is designed as a base class. And I have a struct shape model, which is actually implemented as a class template, and it publicly derives from the shape concept. Shape concept is an abstraction, but the shape model is a wrapper for a real geometry, some geometric shape, like a circle or a square. And the shape model just stores one of these, right? It's given one of these things in the constructor, and it will store that. Circles, squares, ovals, etc. In the base class, we now introduce our operations. Again, it's draw and it's serialize. It is the things that we need. It's the things that we want to do on any kind of shape. And obviously, if shape model inherits from shape concept, it needs to implement these two pure virtual functions. So we implement serialize, we implement draw. The implementation, however, does not contain the details. We simply forward to the implementation. And this is now the place where you explicitly specify what are the requirements on the given types. What do I need? So for instance, I now require a free serialize function for a circle and a square, or whatever I put inside. I require a free function. That, of course, couples definitely much, much less than a member function would do. So free functions. The same for draw. I require a free draw function, something that is implemented somewhere, but, well, it's something that I can use on circles, squares, etc. So that is now the specific definition of requirements. This line, essentially. Now, of course, what you're asking is, where do these dependencies go? Like opengl. Where do these implementation details hide? Well, before we actually had this in the deriving classes of our shape, our strategy, our draw strategy. Now this here, the shape model might be the right place to put it. And I can adapt this. If I want to, I could introduce something like a strategy as well, a draw strategy. I could pass a draw strategy, I could store that, and I could call that whenever it is required. That thing might now contain all the things we need, like colors, textures, opengl specific stuff. That is the thing that we, where all the dependencies go. So I, however, have complete freedom to decide how this should look like. I am in charge. This is not something that the circle implements. This is something that is external indeed. And so this is the so-called external polymorphism design pattern. A very, very interesting, and I believe a very powerful design pattern indeed. That design pattern is not one of these 23 classic gang of 4 design patterns. That is a design pattern that has been introduced 2 years after, in 1996, by Chris Cleland, Douglas Schmidt, and Timothy Harrison. These 3 actually introduced something that allows us to deal with polymorphism slightly differently. So here's the intent. Allow C++ classes unrelated by inheritance and or having no virtual methods to be treated polymorphically, which is exactly what we need for circles and squares. There is no virtual function in there. They're not polymorphic. These unrelated classes can be treated in a common manner by software that uses them. So we externalize the hierarchy. We don't immediately and directly implement polymorphism, but we externalize this. Circles are not polymorphic, but we use them polymorphically. And that actually turns out to be an absolutely amazing and super powerful design pattern indeed. From my personal point of view, perhaps the most important design pattern from today's perspective. Interestingly, it's not that well known, but amazingly powerful. So this external polymorphism design pattern allows any object, even integers, to be treated polymorphically. It extracts implementation details, and quite a bit. You've seen that circles actually don't know anything about drawing, still we can draw them. It removes dependencies to all operations, any affordance, and it also creates the opportunity for very easy extension. You can very easily add triangles and ovals and all other kinds of types, and you can also very easily switch between different kinds of drawing. You've seen the draw strategy here, allows you to do virtually anything. You can put this together like in a Lego game. All right, so that is a very good start. But of course, we now need to continue. I just said that we expect free functions. And so eventually we need to provide them. I provide serialize and draw for circle, and I provide these two functions for square as well. That is now the functions that we need, because that is what we defined as a requirement in this external polymorphism design pattern. And of course, there can be many implementations of these functions, many indeed. There can be an opengl implementation, a metal implementation, a 3DX implementation, you name it. There doesn't have to be one implementation. You can choose between them by including a different file, by linking a different file, and you have the ability, because of that strategy, to also decide that on runtime, kind of. So super powerful indeed. Now, we can also draw, again, a vector of shapes. In this case, it's shape concepts. And that is what I now use in the main function, which admittedly looks a little more difficult. So in order to make our life easier, I now have to use this type alias shapes for vectors of unit pointers of shape concept, now our base class. Then I provide a strategy, actually by means of a lambda, just to show that I have all the options on the table. This is where I set a color, some color, the opengl color, whatever we have. And this is where I now call draw. Now here's the circle, I pass a color, opengl color, whatever. All right, then I have an empty vector, and I slowly but steadily introduce shapes. So I make a shape model of a circle and the draw strategy. I pass the circle and the strategy. I do the same for a square and a second circle, and then I can indeed draw all of them. Three nicely drawn shapes. That should already be pretty fascinating indeed. I know it's not beautiful yet. We'll go there. But circles, indeed, are totally independent of drawing. I supply the draw extra. But at the same time, I don't have to implement that code in a lot of inheritance ways. I can simply pass that at that point very, very easily, very conveniently. At this point, I decide how I would like to draw my thing. Nice, nice indeed. It's very, very strong decoupling. It's totally loose coupling. Circles are totally oblivious of drawing, and yet I can supply it with anything I want. Very nice indeed. However, again, C++ developers are very hard to satisfy, and the use is not nice. Really not nice. It's pretty convoluted. We again have a lot of make uniques, a lot of pointers, and the fact that we have now this artificial shape model class still doesn't make us particularly happy. So let's improve that. And let's move towards what we call type erasure. Because we just have used one design pattern yet. In order to make this truly modern C++, in order to properly wrap that, we now do the thing that you would expect. We wrap this properly inside a class called shape. And shape concept and shape model now move into the private section of that class. Now, you're relieved that suddenly the struct is not public anymore. It is indeed not private, and now we don't care about the fact that it's the struct anymore. It's now a private implementation detail of that shape. Now, what does that shape do with these two things? Well, in the public section of that class, I now introduce a templated constructor. A templated constructor that takes any kind of geometry, a circle, a square, a rectangle, whatever, and any type of draw strategy. That can be a lambda. And note it, it's not a pointer to base. It's any type that you can use in a specific way. That constructor, thanks to template argument deduction, can easily create the right kind of shape model. So we say new shape model. We use the geom shape, we use the draw strategy, we create the right kind of model. That shape model, however, again, is a concept. And so we now internally store this in form of a unique pointer to shape concept. And we give it a name. That may sound familiar, pimple. So this constructor now creates kind of a bridge. That constructor, at the point it is instantiated, creates exactly the right kind of model that brings all of the dependencies together. You don't have to do that. The compiler will do that for you. It's a template after all. And it will create the right kind of model that I can store in an abstract fashion. That actually here is now the bridge design pattern. And now we have erased types. We actually, at this point, inside the shape, don't remember anymore what we got. Okay, could have been a circle, could have been a square. I don't remember. All I know is I have this shape concept. That's it. So we have erased the type inside this class. All right, so thanks to bridge, we now indeed have one foot in the door to actually have the real type. We have this abstraction with all the virtual functions, but we don't know it directly anymore. Hence the name. All right. Now, of course, that type, that shape type, should have the same interface that I also expect on my circles, squares, etc. So on the geometric shapes. So I do not introduce member functions, serialize and draw, but I introduce free functions. I do that in a fashion that may be unfamiliar. I do this by means of nested friend declarations, kind of hidden friends. So I introduce a free serialize and a free draw function into the surrounding namespace, inject them into the surrounding namespace. Still, this is not something super complicated. It just resembles the interface that I expect anyway. But these functions now are responsible to actually trigger the effect. This draw function, for instance, on the given shape, that would access the pimple, so my data member. On that pimple, it would call draw, the abstract virtual function. It would pass all the necessary arguments. And so that function would not draw the real thing, the circle, the square, whatever. So by means of that function, we trigger the polymorphic behavior. And once again, it's not the circle that is polymorphic. We've added this polymorphism by means of the surrounding thing. All right, we are almost done. We're almost done, and it already starts to resemble a pretty interesting implementation indeed. However, we also have to deal with the special member functions. Now, the destructor, by the way, that is trivial. We own a unique pointer. That one is default. The move operations are also default. They're simple because we own a unique pointer. The copy operations are the ones that pose a little bit of a problem. If you want to copy one of these shapes, then all we have in our hands is a pointer to base, an abstraction. And well, it's called type erasure for a reason, as I explained before. We don't know what we have. So we cannot easily create a copy of that. And of course, we do not want to artificially, or we don't want to copy the pointer. We really want a deep copy. After all, it's value semantics. So we need one more thing. We need one more thing to actually make this work. We need another design pattern. And that is the prototype design pattern. So you might actually know that. It is easy to recognize if you do see a clone function. In the base class, in the shape concept, I introduce clone, which returns a unique pointer to shape concept, so a pointer to base. It's pure virtual again, and it needs to be implemented in the derived class. In the derived class, however, I have a very good idea what I need to do. I need to copy myself. So I use my own copy constructor. I copy myself. Again, I say make unique. I return the copy of to myself as a pointer to base. And there it is, the copy, the abstract copy. The prototype design pattern essentially implements virtual copying. So please don't use copy constructor, definitely also not the copy assignment operator for that purpose. Use prototype. So clone is not a keyword, but super attached to this particular design pattern. It kind of acts like a keyword. All right, with that, we now indeed have everything tied together. We have a value type called shape that can be copied, that can be moved, and that represents an abstract kind of shape. With everything it needs, it knows about drawing and of course also about serialization. Everything's in there. That means that we can, again, draw all shapes, but now that function already looks simpler. We have no pointers anymore. We have a vector of shape. Now we have a vector of values. And so if we go through all these values, we can simply draw them by means of the interface we've now decided on, draw shape. Pretty amazing, beautiful. And still it's doing exactly the same thing. And the main function, I believe you admit, is so much nicer, so much more beautiful than the one that we've seen before. Again, we have a type alias called shapes for a vector of shape. We again have some way to draw something. Okay. But this time we simply create very easily circles with the according draw strategy. A square and another circle. And of course, you can pick different strategies. This is for the sake of shortness, sake of simplicity. So we create different kinds of shapes very, very naturally and intuitively. Yes, we have to provide a dependency at this point, but still very easy, very readable, and almost natural. So we have a vector of shapes called shapes. So what do we push back or place back in that vector? Well, a circle. Intuitively, for anyone, this is a shape. Yeah, naturally, it should fit into that shapes thing. And a square, too. It's a shape. From a language perspective, it's already absolutely beautiful. So value semantics is the modern aspect of C++ in this case, definitely. All right. Now, the design analysis. Why is this so much stronger from a decoupling point of view? If you now take a look at a UML diagram again, we have 3 levels. We didn't change anything from that property or from that perspective, but we, of course, adapted the players. The shape abstraction is now the class that I've explained for a couple of minutes now. That is now this type erasure class, the one with a templated constructor and one with a shape concept and the shape model nested classes and a pimple. This is on the highest level. That is the abstraction. That is, again, just the set of requirements that I have to deliver. But I don't have to deliver these directly in circle or square. No, these classes actually still don't know anything about their operations. No dependencies whatsoever. I now provide this on the lowest level possible by means of the actual implementation. This draw will now bring together the requirement from here and the according type, circle, or this draw function, of course, the square. Of course, it's a slight simplification because there's one key player that I don't show yet, and that is the code that is generated by the compiler. The compiler generates our shape model for a specific given shape. Let this be circle or square. That class, the bridge, the injected code, is of course the one that adapts, that brings and binds all of these things together. But again, it's generated code. It's not something that you have to write. The compiler will take care of creating the right thing for you. And this is why this provides such a strong decoupling. It's actually truly amazing how strong the decoupling is. It's so loose coupling that some people feel it's It's too loose coupling. It is very strong decoupling. And so I give the word to Eric Nebla. He actually twittered about type erasure a couple of months ago, so in 2020, and he had the following to say. If I could go back in time and had the power to change C++, rather than adding virtual functions, I would add language support for type erasure and concepts. Define a single type concept, automatically generate a type erasing wrapper for it. And perhaps you have now an idea why he said that. And I, by the way, totally agree with Eric. I agree that this would be so much better, so much stronger, so much more natural. However, we're not there yet, of course. And I totally agree with you if you say, yes, the technique is nice, but I have to write so much code. Well, we can all hope that eventually we will move in that direction and that the compiler will generate something for us. Take away all this boilerplate code for us and create what we actually ask it to create, more automatically than today. All right, so you've done an amazing job by now. We've used type erasure to extract implementation details, again, to create the opportunity for easy extension, yes, and you have still perfectly separated interfaces. It's such a loose coupling, it's so extensible at this point that it's hard to imagine how it could be even better. And of course, we have also, again, dealt with duplication quite nicely. What we've now achieved is that we have removed all dependencies to operations. Very, very nice indeed. We've all removed all inheritance hierarchies, public hierarchies, of course. There is one, but you officially don't know about it. Officially, there is no inheritance anymore. You don't have to inherit yourself from anything. There's hardly any pointers, perhaps even no pointers left. And there's no manual dynamic allocations left. You don't have to use make unique for hundreds and thousands of tiny little things. Nope. That may be handled internally. And of course, we don't have to explicitly manage lifetime management anymore or deal with lifetime management anymore. That is done by the wrapper class. That is already taken care of. Nice. We make our lives easier. And as a last point, and I know this is now the controversial aspect, we've actually improved performance, and potentially quite a bit. The obvious thing is that there is only one virtual function, not two like in the strategy design pattern. There is only one. That is obvious already. However, everything else is, of course, now kind of another talk. Still, there's one idea that I would like to give you right away, just because it's so easy to imagine. We have always used make unique inside the shape, which was my design choice. It was simple to explain the technique. But of course, now that it's a class, you have all the options to do whatever you want to. So we could actually provide a storage policy for shape and tell the shape how it should acquire memory by means of new, by means of using a static buffer, perhaps by means of a hybrid approach, small things stored inside, else it's allocated. You have now all the options on the table. Storage policy. And yes, that is a strategy, of course. There's other talks on type erasure that talk about this performance aspect. So especially, so there is a talk by Zach Lane, for instance, there's a talk by Arthur Dwyer, and especially the talks by Cy Brandt and basically all the talks by Eduardo Madrid, they deal with performance. So if that is something that you're interested in, about implementation details and how to vary things, then this is just the right talks for you. Yeah, the successor talks. Hopefully, I could just make clear why this technique is an amazing addition to your code base. So, still, can you save all the trouble writing this yourself? You can. There's a couple of libraries like Zoo, Dino, and also Boost Type Erasure that actually deal with type erasure in a nicer way. You don't have to write that much code. Take a look. Perhaps this is what you like, and else you still can, of course, implement this yourself. As a summary, type erasure is a templated constructor that creates this bridge automatically, plus a completely non-virtual interface. Types no longer have to be polymorphic. we treat them polymorphically very nicely. And it is a combination of external polymorphism, bridge, and prototype. These three design patterns. And I believe it's definitely one of the most interesting design patterns today. I believe this is something that you can pretty much apply to every inheritance hierarchy you have, and by that gain decoupling. That is the one thing we're looking for, and therefore I feel it's so interesting. So type erasure is definitely significantly reducing dependencies, enables you to use value semantics, which is the modern aspect here. It definitely improves performance if done properly, and it improves readability and comprehensibility. My opinion, maybe something that is subjective, but I hope you agree. It eases maintenance, and for all of these reasons, for all of these good reasons, in other programming languages, that is the default choice for providing dynamic polymorphism. C++ is not there yet, but hopefully we will be eventually. Now, you hopefully do realize that talking about design is pretty interesting, and there is so much more. Now, this was a glimpse on the surface. Now, Jens, or Meeting C++ as a company, and I have agreed to that. And so there is also a couple of training classes on design patterns. Perhaps you're interested. We do this a couple of times a year. The next thing will be in February, mid of February, in case you're interested. And of course, type erasure will be part of that training too. Okay, then, thank you very much for the attention. And I'm definitely very happy to take a couple of questions.
Yes, thank you very much for the talk. That was interesting. And wow, I knew Klaus would deliver, but that's really interesting code. So we have 2 more minutes, and I'm okay if we go like a little bit of overtime. Because the next session is 20 minutes
Just
away.
pick the questions you feel are most
yes.
appropriate.
So to the audience, if you want to upvote questions, that helps me choose, because there is not a lot of upvotes in the questions. So more upvotes helps me choosing. There is, of course, the obligatory question first. What are the performance implications on compile time?
So I didn't explicitly measure, but using the technique, for me, didn't reveal any problems. And I believe the reason is that there is not a lot more to do. What you need is this templated constructor that, of course, needs to be generated. And of course, you need a specific model. If you have a lot of variations, of course, there's a lot of models. That may be kind of bad indeed, but generally, you don't do a lot more. If you would do this manually, you might have many more code, much more code. You might have many more base classes. You may have many more hierarchies. I believe this actually saves you trouble. But I have to admit, I never benchmarked because I never found this to be a problem at all. So compile time, okay, definitely.
Okay.
By the way, I'm speaking about my code. I'm not speaking about boost type erasure, for instance. Okay. That is much more template heavy. That may be different.
Yeah, that could be the case. What would you say are the pros cons between the version you've shown us today and a hypothetical version that uses std_any to do the type erasure and the switch with the anycast?
So std_any is implemented by means of type erasure, which means if you wrap type erasure around type erasure, you have twice the runtime effort. That actually was something that was published at some point, that you have some function pointers that do this anycast, and as a member you store any. I don't like that idea at all, because I feel this is a bazooka approach to something that's much more simple. So wrapping type erasure in a type erasure approach feels like missing the point. I feel the code I've shown is simple enough that you can write this for a couple of things. You don't need this additional simplification, which definitely draws in RTDI, exceptions, dynamic memory, and the anycast is maybe a dynamic cast also. Not such a great idea from my point of view.
Yes, there's a very good question. I am often haunted by the type erasure. It is nightmare to search for a single specific operation for a class circle in a complex and large code base, especially if you are not sure about the exact name of it. Is there a solution for that? The lack of centralized interface can backfire.
Of course, you decide. In type erasure, you have decoupled, so you decide what you actually expect. You can, if you want to, also put things into a circle. You can expect a member function. Of course, that usually creates dependencies. That is exactly what you want to solve. Usually the problem is that your IDE might not point out that the operation is available as a free function. So I don't think it's a design issue. It's more like a tool issue. So if you use CLine, for instance, CLine also shows you what is available in form of free functions, if you want to. I believe that Visual Studio by now has the same thing. It may be more of a tooling issue than it is a design issue, but I definitely get the point. Maybe you find a compromise between the two extremes.
Is there any aspect of C++20 that will improve this approach?
There's definitely something that it can do. Concepts help. So I've basically stripped this to the very basic points. I've not checked specifically that the type that I get, this geom type, is truly a geometric type. That is something that concepts can do. The error messages tend to be nicer. You tend to properly constrain all of these template functions. That is a very reasonable thing indeed. Again, I kept the code simple, but I believe this actually is not a lot of overhead. The concept could be a couple of lines, so 4 or 5 lines for this example, and I could use this in 1 or 2 places in the class. That would be a very reasonable addition, yes.
Okay, then I'd say we are doing the applause for Klaus. Thank you very much for giving this great talk. I see there's still a bunch of questions which have not been as popular, but probably want to be asked. I think you might be able to answer them with typing, but also I think you wanted to go to the lounge. So yes. If you want to have any questions or probably a debate with Klaus about this, there is the launch, and if you would like to have this a bit more extensive and more on also on patterns, then there is a course which I put in the chat, and you can find when you go to his talk. That's linked. Okay.
Then thank you, Jens.
Yes.
And I'll see you in the launch.
Okay. Then I'm going to stop stream, and that's doing it now.